This ECE 201 lesson is titled Linear Circuits and the Use of Superposition. We're going to bring to the table another method of solving circuits. It applies only to linear circuits. So first of all, we will define a linear circuit, and then we'll see how in principle and with one example, how superposition can be used to solve for a particular circuit variable of interest. Our motivation for discussing linearity in the context of electrical circuits is really to gain new methods for solving circuits. Now, up till now, we've talked about circuit elements such as resistors, where V equals IR. There's a linear relationship between voltage and current. We've discussed circuits with nonlinear devices such as light-emitting diodes, where there's an exponential relationship between current and voltage. For either linear or nonlinear, the basic ideas of connection constraints, i.e. KCL and KVL, and element constraints hold, and therefore methodologies based on those connection constraints and element constraints like mesh current analysis and node voltage analysis hold. However, if we know that we're dealing with a linear circuit, we have new methodologies at our disposal. Things like superposition, the unit response method, Thevenin's theorem. Today the focus is going to be on superposition, but before we get to that, let's define carefully what we mean by a linear circuit. In discussing linear circuit, one important attribute, indeed one key attribute, is homogeneity. We said the output of interest may be a current or voltage in the circuit. Let's designate that output by Y just for generality. And we've said the inputs will be sources of electrical energy modeled as voltage sources or current sources, and let's designate the input as X. So there will be a relationship between the numerical value of the input and the numerical value of the output. If the X, the input, represents a voltage source of a certain value, and the output variable Y represents the current through a particular resistor, there's going to be a functional relationship between them. Now, homogeneity is the property that if you increase the input variable by a factor k, where k is some constant, then the output variable increases by that same constant. If I have a 1.5 volt voltage source with a certain output current, and I quadruple the voltage source value, then I will also quadruple the output current. This is homogeneity, key property of linear circuits. But homogeneity is not the only required property of a linear circuit. Let's broaden the picture to include multiple inputs. For example, X1 could be a voltage source and X2 perhaps either another voltage source or a current source. And let's consider that the functionality of the circuit is such that if X2 is set to 0 and only X1 is acting, or we say only X1 is on, then Y, the output, is equal to f of X1. Conversely, if X1 is set to 0 and only X2 is on, then Y is equal to f of X2. Well, this brings up the second property we will require of linear circuits, namely additivity. For the property of additivity to hold, the output when both sources are acting simultaneously must equal the sum of the output when only source X1 is on, X2 having been turned off or set to 0, plus the output when only X2 is on, X1 having been set to 0, or in other words, turned off. We can combine the properties of homogeneity and additivity rather elegantly into one equation and say that a circuit is linear if and only if the quantity f of ax1 plus bx2 equals the sum of the separate quantities a times f of x1 plus b times f of x2. A and B being constants. So there are two properties associated with linear circuits, homogeneity and additivity. Associated with homogeneity is a circuit solving method called the unit response method. Associated with additivity is a circuit solving method called superposition. Now let's take a look at how we would use superposition to solve circuits. Let's consider in our mind's eye a circuit that has a 1 amp current source and a 100 volt voltage source. And let's say the output is the voltage across a particular 100 ohm resistor in the circuit. By the additivity product, we may solve the circuit by what we might describe as a divide and conquer approach. First, find the output just due to the current source with the voltage source set to 0, and then find the output just due to the voltage source with the current source set to 0, or vice versa. In either case, we can then add the two separate contributions together to find the response for the original circuit. Let's take a look at such a circuit. We have one drawn here on the board, and we see a voltage source, a current source. Those are the inputs or excitations, and the output will be the output voltage across this. Now, to use superposition, I want to say that V out is partly due to the voltage source, partly due to the current source. Let me turn the current source off. Let me set the current source equal to 0 and find the output just due to the voltage source. How do I set a current source to 0? I set its value equal to 0. Zero current is the same thing as an open circuit. So how about we simply replace this current source by an open circuit. Now we've turned that current source off, or sometimes people say they've killed the current source. We're going to find the output just due to the voltage source. We can simply use voltage division. 100 volts divided equally across 200 ohm resistors, V out is equal to 50 volts. Let's call that V out 1 because that's just due to the first source that we're considering. Now let's see what the output would be just due to the current source acting. Here I've drawn the current source back in. I want to set the voltage source equal to 0. 0 volts is a short circuit, so let me replace the 100 volt source by short circuit. Easily done. And now I have a current division problem looking at me. This 1 amp source sees two branches of equal resistance. Half the 1 amp will flow to the left, half will flow to the right. So we have a half an amp here flowing in this direction. By Ohm's law, the voltage due to the current source turns out also to be equal to 50 volts for this particular example. So now we know that just due to the current source we get 50 volts, just due to the voltage source we get 50 volts. We can add them together and say that the total output with the two sources acting together is 100 volts. Or to write this on the board, we can say that V out is equal to V out 1 plus V out 2, which is equal to 100 volts. That's an example of the use of superposition. Divide and conquer, work with simpler circuits, and then add the results together. This concludes our lesson on linearity and the use of superposition in circuit analysis. It's another very useful technique to use. It only applies to linear circuits. In this lesson, we saw how to define a linear circuit and how one of the properties of that definition, namely additivity, led us to a new method of solving circuits, namely a divide and conquer approach in which we consider the contribution of just one source at a time, therefore simpler circuits, and add up the responses at the end to get the final answer.